Hi everybody, how we all doing today? This is our video lesson for graphing motion, which is section number 4 for our first unit here. When we graph motion, we're going to do this in two ways. We're actually going to do this with what we call position versus time graphs, and then we're also going to do velocity versus time graphs, but that'll be in a different video here. So, what is a position versus time graph? Where does it come from, right? Well, a position versus time graph is a way to represent the motion of an object on a graph. And when we're going to graph that stuff, we're really going to start with an idea that we were talking about in the past in our ticker tape diagrams. All right. So remember with the ticker tape diagrams, what we were doing was we were representing the motion of an object, all right, as it went from one place to another. And we were doing this by placing dots along our entire path, right? And if we were doing something that had a constant velocity, if we all remember correctly, then we noticed that the dots were all evenly spaced. Now each one of these dots, remember, they represent 1 second in time, and then this is the place that that object would have been located at that second. So maybe at our starting point, which is 0 seconds, we might have started at 0 meters, all right? And then 1 second later, we might be located at 1 meter. And remember, we went 1 meter in 1 second, so this would be like having a velocity of 1 meter per second. And remember, that's that same displacement of 1 meter every second. So my next position at 2 seconds might be 2 meters, right? 3 meters at 3 seconds. 4 seconds, we have 4 meters. And we could do this for a long time, right? But I'll stop here at 5 seconds. And the idea is that the object is moving at that nice constant rate, and so we see the distribution of the dots are exactly the way we see them. They're nice and evenly spaced out. So how is it that we take this and we put this on what we call a position versus time graph? All right. Well, up here at the top, these are our positions. All right. These are the places that the object is located relative to 0 meters at each second that ticks off. And this down here is the time. And so really what we have are our x components on a graph. Those are going to be our times. And then we're going to have our y components on our graph. Those are going to be our positions. And we're just going to graph these against each other so that they're the x and y components of the points that are on the graph. So let's graph the position versus time graph for our first example here, this first ticker tape diagram that we have. So I'm going to flip back and forth between a nice piece of graph paper here. So if you need a piece of graph paper, hey, just find one over on the side table there. All right. So we have two axes here. All right. And like I said, this is a position versus time graph. So time is going to be located on the x-axis. All right. Time, remember, is t, and we're going to measure that in seconds, right? And then position, all right. All right, that's going to be along our y-axis here. Remember, positions are x's, and those are measured in meters. So a lot of the time what we'll see on a graph is that we'll see x on the y-axis, and then we'll see a t on the x-axis, which can be a little confusing at times. But remember, x means position. All right, so let's take the data from that previous slide here. All right. And basically what we're going to do is at 0 seconds, we're going to place a dot at 0 meters. At 1 second, we'll do it 1 meters, 2 seconds, 2 meters, 3 seconds, so on and so forth. And we'll graph all of this motion. All right, so assuming that each one of these blocks up the side here, we'll make this one, we'll do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 marks here along our y-axis. All right. We'll go all the way up to 10 meters here. And then down along our y-axis, we can really choose any scale that we want, but why not stretch it out a little bit so that we use the whole graph? So I'm going to go about 4 blocks here until we have 5 seconds. So as we go to graph these things, we're just going to put our data right exactly the way that we saw it on the previous slide. So I have a dot right here at 0, 0. All right. At 1 second, I will be traveling, I will have gone 1 meter. That's my new location. That's my new position. So my new position is at 1 meter at 1 second. At 2 seconds, I'm going to be located at 2 meters. That's my position. All right. So position, time, right? Position, time. My next position will be 3 meters at 3 seconds, 4 meters at 4 seconds, 5 meters at 5 seconds. And if we go ahead and connect all of these dots, and if I did a nice actually straight line, right? So if we go ahead and we connect all of these dots, then we're going to notice that we get a nice straight line out of it. That's a really terrible line, but we see that we kind of understand our point here. So what's the significance of this line, and what is it telling us? Well, the shape of these graphs is actually telling us about the way that the object is moving. Now, if we think about our ticker tape diagram, this is for an object that's traveling at a constant velocity. So on a position versus time graph, constant velocity looks like a straight line. And that's really cool. And there are a lot of things that we know about straight lines, and that's one of the things that we can use this graph for. So if we're looking at this graph, some of the important things about lines are things like slope. So what does the slope really mean on this graph? All right. So if I look at what slope is, remember slope is rise over run, right? So my rises here are changes in position. Those are my y components, are positions. So as I rise, I'm changing my position. And as I go along my run here horizontally, right, I'm changing my time. So my run is a change in time. So if we look at that, that should look really familiar, because a change in position and a change in time really is the velocity. So the slope of a position versus time graph is the velocity. This might be the #1 most important thing that you can pick up from a position versus time graph. So all we would really have to do if we saw one of these graphs, right, would be to do our rise over our run for any 2 points along our line, and we should be able to find our slope here. And if we find the slope, that should be our velocity. And if we look at this graph, right, the rise the rise starts here at 0. Sorry about the cough, guys. All right. It starts at 0 and it ends at 5. So my change in position is from 0 to 5, right? So delta x is positive 5 meters, right? And my time changes also by 5 seconds. So delta t is equal to 5 seconds. So that means that our slope is 5 over 5, and that's just 1 meter per second in the positive direction. So So this is what a positive velocity of 1 meters per second looks like on a position versus time graph. So how does that change with different velocities, right? So I'm going to go back to this slide and let's add another ticker tape diagram. All right. So we already did 1 meter per second. What does it look like if we do 2 meters per second? Well, if we remember back on our ticker tape diagrams, right, then a velocity of 2 meters per second is faster. And one of the things we said about that was that the dots should be farther spaced apart. So if we're going at positive 2 meters per second, right, then what's going to happen is we're going to go a displacement of 2 meters every second that ticks by. So at 0 seconds, we'd be at 0 meters. At 1 second, we will have traveled a displacement of 2 meters. So now our location, or our position, is 2 meters. And then at 2 seconds, we would be at 4 meters. At 3 seconds, we would be at 6 meters. At 4 seconds, we would be at 8 meters, right? 5 seconds, and we'd be at 10 meters, all right? So we see the spacing of the dots as a little bit farther apart on our ticker tape diagram. Well, what do we get whenever we put this on our position versus time graph? Just to kind of help us out, let's label this one A, and let's label this one B, and we'll put both of these lines on the same graph with each other. All right. So this one right here, this is my line A. What about line B? What does this look like? Well, this one is also going to start at the 0, 0 mark, right? But what's different is that after 1 second, I'm now going to have a position of 2 meters. And at 2 seconds, I'm going to have a position of 4 meters. At 3 seconds, I'm going to have a position of 6 meters. At 4 seconds, I'm going to be located at 8 meters. And at 5 seconds, I would now be located at 10 meters. And so the lines, again, they're both straight because they're constant velocities, right? But what's the difference between the two? Well, B has a greater slope. It's steeper than A is, right? And that makes sense because if slope is your velocity, the bigger your slope is, the greater your velocity is. So B has a greater velocity than A because it's steeper. And the reason it's steeper is because our displacements are bigger as time goes on. So here we're displacing by 2 meters every second, but up here we're only displacing by 1 meter every second. And that causes our graph to be a little bit flatter, right? Takes a second for this to jump, but it causes it to be a little bit flatter for A than it is for B because it has less velocity. So just by looking at a position versus time graph, we can tell whether an object is going faster or slower just by the slope of the graph. So then let's look at a couple other weird situations that happen with position versus time graphs. All right. So let's say we had a line that looked more like this. Oh, that would not be B, that would be C. So let's call this line C, all right? And we might ask ourselves, all right, what is this object doing? Well, it has a straight line, so that must mean that it's traveling at a constant velocity. But this time, the slope is actually in the opposite direction. So if these guys had positive slopes, right, then this one, C, must have a negative slope. And if it has a negative slope, that must mean that it has a negative velocity. So that could mean a lot of things depending on what object you're looking at, but it means that it's moving in the negative direction. So it's the shape of the graph, that flatness or the straightness of the line, right, that's telling us that it's traveling at a constant velocity. If it's steeper, then that means it's a greater velocity, and if it's flatter, that means it's a smaller velocity. And then if we have a negative velocity, right, we're going to see a negative slope. Pretty cool, right? One more of these. Let's look at one more example. What is this object doing? if it has a nice flat line. Well, this object is not moving at all. It's stationary. And we know that because of two reasons. First, it is perfectly flat. That means or it's perfectly straight. That means it has a constant velocity, all right? Because it's a straight line. But because it's a flat horizontal line, that means it has no slope. And if it doesn't have any slope, that must mean that it has a velocity of 0 meters per second. Well, velocity of 0 meters per second means something is not moving, and that's what this thing is doing all the time. It's always located at the same position. This would be what, the 12-meter mark. So it doesn't matter what time I look at it, it's always located at 12 meters. That's like literally the definition of not moving, is always being in the same place. So a flat line on our position versus time graph means it has no velocity or it's not moving. And that's position versus time graphs. So these are all pictures of things that are traveling at a constant velocity. What if it's not traveling at a constant velocity, right? What if it's accelerating? Well, there's really 4 cases for that to happen, all right? And we're going to draw all 4 of them here. So 2 things that we have to be really careful of, all right, are direction, all right? Because an object could be traveling in the positive direction, or it could be traveling in the negative direction. And then an object could be traveling in the positive direction and speeding up, or it could be traveling in the positive direction and slowing down. You can do the same thing for the negative direction, right? So how do we tell from the shape of a graph? Well, let's look at a situation where it would be accelerating, all right? So what does a ticker tape diagram look like for an accelerating object? We have an example of that, all right? We know that when it first starts off, it's going to be going slower. So let's say we're moving in the positive direction, all right? And let's say that we're speeding up. Then what would happen is we would see that our dots would be pretty close together to start. But as time goes on, they would get farther and farther and farther apart. All right, and we remember this back from ticker tape diagrams. Let's use one of the kinematics equations that we just learned in the last section. All right, so displacement is equal to the initial velocity of an object times the time plus 1/2 at squared. All right. Now what we can actually do is we can use this to help us find the location of the object at any time that we want. Now let's say we're starting with an initial velocity of 0 meters per second. Then that means that this whole term is just 0, and we could say that our displacement is 1/2 times the acceleration times time squared. And then let's make it super easy on us. All right, so we have an initial velocity of 0. Let's make our acceleration 2 meters per second in the positive direction. If we want to speed up in the positive direction, then our acceleration needs to be also positive. All right? So how does that look? If I plug in that acceleration, right, of 2 meters per second squared, then I can pick any time that I want, and I should be able to calculate where my position is. So what happens at 0 seconds? Well, 0 squared is 0, times 2 is 0, times 1/2 is 0, so that would be 0. 0 meters. So at 0 meters, at 0 seconds. What about at 1 second? All right. So at 1 second, then we would substitute 1 into this equation. 2 meters per second squared, right? 1 second. So 1 squared is just 1, times 2 times 1/2 is again just going to be 1 meter. So at 1 second, we're located at 1 meter. What about at 2 seconds, right? We plug that in. Two squared is 4, times 2 is 8, times 1/2 is 4. And now we're located at 4 meters. So at 2 seconds, we're at 4 meters. And if you're noticing any kind of pattern here, at 3 seconds, it'll be at 9 meters. At 4 seconds, it'll be at 16 meters. And then at 5 seconds, it'll be at 25 meters. So if we go to graph this on the other page, what we're going to notice is that the dots are no longer evenly spaced on our ticker tape diagram. That's also going to change the way that things are spaced on here. Now I'm going to need this thing to go all the way up to 25. I don't know that I actually have 25 squares on here. All right. All right. So I'll make each one of these 2 meters. All right. And the next one will be 4, 6, 8, 10 meters, 12, 14, 16, 80, 18, 20 meters. All right. And this will be 20. Oh, sorry, 22, 24, 26. All right. And then down along the bottom here, again, we'll label our seconds. So 1 second, 2 seconds, 3 seconds, 5 seconds. So if we go to graph these points, we're going to see a point at 0, 0, right? Then at 1 second, we're going to be located at 1 meter. At 2 seconds, we're going to be located at 4 meters. At 3 seconds, we're going to be located at 9 meters. At 4 seconds, we're going to be located at 16 meters. So at 12, 14, 16. Right? And then at 5 seconds, we'll be at 25 meters. And what do we have here? Now we don't have a straight line anymore. Now we have a curve. And this is a very specific kind of curve. This is actually a parabola. And that comes from the fact that the position is actually related to the time here by a quadratic function. All right? So that when we plug in all of those times, we're going to see that curve here. So this object with this, whoa, that went a little bit too far. This object with this shape, this is an object that is traveling in the positive direction and speeding up. And we know that for one very, very good reason, actually 2 very good reasons here. So as we look over time and we look at our y-axis over here, right? As time moves forward, we're seeing that our positions are getting more positive, right? Because we're going up on this axis. So that's what tells us, right? That's what tells us that we're moving in the positive direction. And we know that we're speeding up because if we look at the shape of our curve, right? What's it doing? It starts out really, really flat, right? If I were to draw a line here, it's like, it's really, really flat. But as time goes on, it's getting steeper and steeper and steeper and steeper. And remember, the steeper that something gets on one of our position versus time graphs, the faster it's going. That's because our slope is getting bigger and bigger. So this graph is moving definitely in the positive direction because our positions are getting bigger. And it's getting faster because we notice that our line, our curve, is getting steeper and steeper and steeper as we move off in time. And so this is what speeding up in the positive direction looks like on a position versus time graph. And we can kind of look at all 4 situations for acceleration kind of using those ideas. So what would it look like if we were moving in the positive direction but we were slowing down. Well, the positive direction means that we should be getting bigger and bigger and bigger along the y-axis. But when we move through time, if it's slowing down, then our graph ought to be getting flatter and flatter and flatter and flatter, right? So what does that look like here? Well, that has a very specific shape, right? So we should be moving up, and we should be getting flatter. So now our parabola looks like this. And so that's what it looks like when an object is moving in the positive direction, but slowing down. So we're moving in the positive direction because our positions are getting more positive. We're moving up along that y-axis. And then we're getting slower because our graph, as we go here, is getting flatter and flatter and flatter and getting closer and closer and closer to perfectly horizontal. So what about if we move in the negative direction, right? So if I move in the negative direction, that would mean that as I go on my y-axis, then my numbers should be getting smaller. So they should be going more in the negative direction, right? So here we're moving in the negative direction. And let's move in the negative direction and speed up. Well, that should mean that my graph, as it curves, should be getting steeper and steeper and steeper and steeper, all right? So that means it's going to start out flat and then get steeper and steeper and steeper as time goes on. And so this is what it looks like. It's kind of not a good parabola, because remember, parabolas, they grow fast, right? So this is what it looks like when an object is speeding up in the negative direction. And then finally, we can look at slowing down, right? And in this case, again, we want to be moving in the negative direction as we go, but this time we want it to be getting flatter. So we want it to start out steep and then get flatter and flatter and flatter and flatter. And this is what it looks like when we're slowing down in the negative direction. So that's basically everything there is to know about position versus time graphs. First, if you're traveling at a constant velocity, right, you're going to see a straight line. That's constant velocity. When you see a curve, specifically a parabola, that means that the object must be accelerating. Depending on the shape, something could be going faster or something could be going slower depending on your slope. So when a slope is low, when you have a small slope, or it's not very steep, then you have a slow velocity. And when it's steeper, then it would be a fast velocity. And when you're accelerating, depending on the shape of that graph, you might be moving in the positive or negative direction and speeding up or slowing down. You want to be careful, because what's happening on those graphs is that the slope is changing, and it's either getting steeper or it's getting flatter, and that's going to tell you whether it's getting faster or whether it's getting slower. All right, everybody. That was pretty cool. Thanks for coming. I'll see you next time.